by probing quarks and gluons in the atom's nucleus with beams of electrons from the superconducting accelerator. Jefferson Lab has an educational mission as well. The Jefferson Lab Science Series features scientists and engineers who are gifted in making their work not only informative but fun. The Science Series is held once a month in the Jefferson Lab Auditorium. The presentation is live, spontaneous, and unrehearsed.
Good evening, ladies and gentlemen. My name is Dave Couch, and I'd like to welcome you to Jefferson Lab for this final Science Series presentation for the year. This evening, we have with us Chris Ekstrom, who is from the U.S. Naval Observatory. Chris has recently been named the head of the Clock Development Division for the U.S. Naval Observatory, and this evening's talk is on clocks and time. Brief background for Chris. He did his undergraduate work at the University of Washington, where he received a BS in physics. He then received a PhD in experimental atomic physics from Massachusetts Institute of Technology, known as MIT. Doctor?
Hello. Can everyone hear me? Are these on? Okay. See that? Great. I'm here to talk to you about clocks and time, and what we're going to end up doing is, can you hear? I don't think your microphone's on. That direction? There we go. Okay, great. Okay, we'll use the feedback as an example later. It'll come up in the talk. I'm going to talk to you about clocks and time, and my name is Chris Ekstrom. I'm from the U.S. Naval Observatory. Why an observatory and sending someone to talk to you about time? Some of that will become clear later, but it turns out that we are an organization that has been historically interested in navigation products, so getting ships places, knowing where they are. And three main areas we work in are star charts, navigating by looking at the stars, something called Earth orientation, where the Earth is pointed underneath the stars, and timekeeping, and that's the area I work in. So we have a big department called Time Service, and I work in the clock development area of that. And the type of clocks I'm developing are atomic clocks. And by the end of this, you should have an idea of what an atomic clock is and why we bother, and kind of how it compares to a host of other clocks that you deal with on a daily basis, or maybe don't realize you're actually dealing with clocks. So an outline of what I'm going to talk about. And this outline and this talk is going to be roughly in historical order. Not exactly, but pretty close. And when I talk about each new clock, I'll tell you about when people started caring about it or realizing it was a good clock. And something that's interesting is every clock I will show you is being used up to the current day. Even ones which will look quite archaic may actually have quite pertinent uses today. So first, an introduction to clocks. What's a clock? What time is it? That kind of thing. We'll talk about celestial clocks. And those are clocks that use something to do with orbits or planets spinning or moons moving around or the stars or something. And then we'll go on to the pendulum. Many of you are familiar with pendulums. They actually have a very august history in timekeeping. And then the first really big application I'm going to talk about, which is longitude, finding the longitude, or where you are around the globe, not down from the poles, but around. Turns out it's a very difficult problem, and you can solve it with clocks. I'll move on to quartz clocks and atomic clocks, moving into higher quality, more modern clocks. And the final application I'll talk about is the global positioning system, which is really the pinnacle of applications of atomic clocks. One theme you'll see is that the applications I'll pick, and I think really the big targets that clock keeping has been applied in and made its mark in, have been navigation applications. So we'll back up and we'll ask, what's a clock? Any clock, and this is true of all clocks, have two parts. They have some part that repeats itself, that oscillates. It's a periodic system. You can say it lots of different ways in the physics language. It's a periodic system. It's a repeating system. It's an oscillating system. All it means is that it's going to be in one state, and after a while, it'll come back. And you can call those ticks, and you can call those oscillations, anything. And then you have to have a counter, and you count ticks. And now I've told you what a clock is, and that's true of a pendulum clock, that's true of the Earth going around the sun, that's true of atomic clocks. And throughout the talk, we'll identify the thing that's ticking and how we count it and why we care about counting it. Now, one important thing, which may seem kind of pedantic or not important, is you have to decide what your rate means. The second, it turns out, is a defined quantity in terms of some atomic physics properties. But you have to decide what rate is important to you and what your rate means. Maybe a day is important to you. Maybe the season is important to you. Maybe the year is important. And that will also be a theme. So I told you what a clock is. Next question is, what time is it? The simple answer is how many ticks you have in the counter that's part of your clock. And actually, at this point, I should stop and say, if any of you have questions during the talk, feel free to ask them during the talk while they're fresh in your mind, and I'll be happy to digress or clarify what I haven't made clear. So the time is how many ticks you have in your counter. So you have some oscillating system, you're counting ticks, and it's how long it is from some time. And that starting point you picked as, it's 10 seconds from whenever, it's 10 years from whenever, is almost completely arbitrary, unless you have some big event that you cared about, like the sun rising on a certain day, or the last time the wheat sprouted, or something like that. And it really is, if you reset your counter, if you lose the information in your counter, you're really lost. You have to go find some other clock and sync back up with it. The other thing you have to know is you have to pick your units. And that's coming back to, do I care about seconds? Do I care about minutes? Do I care when I get to work? Do I care when I have to plant? And also demand the performance that fits your needs. It may be all you care about is not using up all your daylight hours on planting food and not forgetting to gather some food to eat at night. And it may be what you really care about is synchronizing communications satellites. And those require wildly different performance, and you're going to apply wildly different tools to each of those situations. There's a really neat book I would recommend to you called Time's Pendulum by Joanne Barnett. It's published by Plenum. And it's a look at a lot of the things I'm going to talk to you about, the historical aspects of clocks, and some of the technical details, but really how clocks have evolved through the ages, and why you decided you needed to develop a clock, or why you decided you didn't want to promote this certain clock. And there were all kinds of implications about timekeeping, many of which had to do with the church, and usury and selling time and all this kind of thing. And it's really fascinating. And a lot of the material, historical material, will actually come from that, and another book I'll mention later, which I will recommend even more highly. So our first clocks, celestial bodies as clocks. Now we're going to start dating clocks from when they were used, very early on. We don't have any date for this, really. That's because the first celestial bodies as clock you're going to use is you're going to notice that it turns light and then it turns dark, and then it turns light and it turns dark. And you decide to call those days. And for a long time in history of the human race, that was the only important thing, is that I have some daylight hours, and I can use those daylight hours to accomplish some tasks and feed myself and my family. And then I have some nighttime hours, and I don't have the technology to use those. I'm just going to have to sleep or sit there or whatever. But I really don't have the infrastructure to do work then. I can't go plow a field when it's dark. So you have a periodic system, and you can count years, you can count seasons. And those are the really important things once you become agrarian, is when should I put the seeds in the ground so I can actually get food and not starve. So the main system we're talking about is this one. So this is an old picture, which I thought was kind of neat. And actually has a lot of neat information in it. So it's the sun, and this is the Earth going around it. Obviously, brutally not to scale. But the things you can see are, the Earth goes around the sun, and you all knew that. And that's a year. But you also know that seasons occur, and that's because the axis of the Earth, you can see this line right here and right here, with the poles right there, is tilted. That just means that if you're on this part of the globe, as you go around, You get more sunlight or less sunlight on average in a day, and those are your seasons. And then the Earth all the time is spinning around, and those are your days. So this is a repeating system. The Earth's going to come back to the same spot around the sun. This is our periodic oscillator. The way we're going to count it is we're going to make marks on the wall or in the dirt or whatever. Not in the dirt, but to count years. And days, similarly. You can make marks. Your counter doesn't have to be very fast or very robust. Interesting trivia point. There is this little line which is going straight from the center of the Earth to the sun. That kind of traces out an arc on the Earth as you go around in the seasons. Those are the tropics of Cancer and Capricorn. You see the lines on the map. That's how they pick those points. And one interesting thing to see here is that clearly the length of your daylight hours are going to change over the course of the year. So the amount of daylight you get during the year is going to change. And the key about those I've made a couple times is those are your useful working hours. So what you really care about in your celestial clock's counter is that you get equal parts of the daylight hours. Because you're going to want to spend part of your useful time, I don't know, eating, part of your useful time planting, part of your useful time hunting, and make sure that you get enough done that you don't starve. And the classic device for seeing what time it is a sundial. This is a picture of a sundial. This is actually a sundial made by an artist named Harriet James in England, just to give credit where it's due. And what happens is that you have the sun, and it's up, and this little thing right here, which you can't see the side of, but it's just a triangle sitting right here. That's the tip of the triangle. That's one corner on the bottom. The other corner on the bottom is parked over here underneath itself. It's called a gnomon, G-N-O-M-O-N, and that casts a shadow on the sundial. And you read off where you are along the sundial here, and that tells you what time it is. It's about 9:45 in that picture. Okay, I'll try it. I'll do my kludgy demonstration of a sundial. There's a mag light. Okay, it's the sun, and there's your gnomon. And basically what's happening is the sun's coming up, it's doing this, it's coming down. And that shadow shifts across the screen. I'm not doing a very good job, am I? Shadow shifts across the screen this way. It's exactly what the gnomon is doing, except that you have a much better calibrated system for reading out what the location of that shadow means. And you point that guy north, and basically the sun comes up from way over here in the horizon, and the shadow is cast on this side, and that's kind of 6 o'clock in the morning, and it walks its way around. And the length of the shadow actually tells you what the season is. And there are very, very elaborate clocks which do beautiful jobs of telling you exactly where the seasons are and how far you are from the various equinoxes. They're really amazing devices. And there's a whole field of stellar astronomy, which has to do with building sundials and where it is and how the Earth-Sun system is moving around. It's actually very neat stuff. So sundials give you equal parts of the daylight hours, which you care about, and also seasons, so you want to plant, for instance. And it turns out from very early on, thousands of years before BC, people had water clocks, and they were really pretty good. Now, a water clock is a fundamentally different thing, because a sundial has unequal length hours. It's a clock that ticks at a rate that changes every day. It's a very kind of weird clock. It's rather foreign to the way we think today. So the length of the hour changes from day to day. A water clock ticks at a regular rate. You drip water from one container to another, and you count it somehow. But you arrange things so it drips at a constant rate. And that's much more like the way we keep time now and the way we think about time now. But it was very foreign when you had sundials as the master of how you told time. In fact, there are elaborate correction tables carved in stone in ancient Roman cities about how you correct that obnoxious water clock so it agrees with your sundial. So you have this wonderfully regular clock, which we would pick as, well, that's the right clock, and it's all corrected to match the sundial. Okay, so water clocks. I have a nifty picture of a water clock. This is a famous Chinese water clock. All I could find was a bad black and white drawing, and I tried to color it by hand so you could see what was happening a little better. It's 4 stories tall. It's a 14th century clock built by someone named Su Sung in China. And there's this paddle wheel arrangement here, just like on a mill race if you're grinding flour. Except there's a little cup on the end of each one of these guys. And there's a device right over here that's dripping water in at a constant rate. And you can kind of see the green here, which is supposed to be the water splashing down, but it's a really terrible rendition of water splashing down. But there's a cup here that fills up for a little while. And when that cup gets heavy enough, it trips a little mechanism which releases the water wheel, and it ticks over one more location around. So then this next guy comes into the location and gets filled up. And then it ticks down one more, and this guy is being filled up. And it goes around. And you fill up the cups at a constant rate. And there's a very cute little linkage which kind of weighs how much water is in each cup and trips the wheel, and it goes one more. And then you have a whole bunch of gears and stuff which move these platters around. They're like lazy Susans with little pictograms in Chinese. And from the outside, you see whichever pictogram is in the front in each of those things. That tells you the time. It's a wonderful thing. Other things to notice is there's a really fancy sundial on the top. And that's what they're using to correct everything with and to synchronize with. And you know, this is 14th century. Sundials are still being used. And they're the way that you make sure the clock is running on time in the long term.
Did it have a calendar as well on it too?
This, I assume, would have a calendar. The question was, did this have a calendar as well? There are certainly indications there were a calendar because this little sphere right here is the Earth tilted on its axis, which is used for deciding where you are in the seasons. Translating what you see up here on this fancy sundial, which is called an armillary sphere. So I don't know a whole lot about this water clock. I assume that it told you what day it was as well. Okay, so we've gone through celestial clocks and a little bit of water clocks, although water clocks are also a fascinating subject. Okay, point of trivia. Ancient Romans used to time speeches with water clocks. And there's a very neat little water clock where you basically take a bucket of water and you put something that looks like a flower pot in it with a small hole in the bottom. And you wait for the flower pot to slowly drip water and it sinks, and then that's your timer. It's like an egg timer. And they used to time speeches for the politicians. And that's probably where the origin of the first water comes from. You schedule the best speech first. And there's this old phrase called "of the first water." And that probably means the highest quality speech from when you're timing things with a water clock. And the next clock I'm going to talk about is the pendulum. And it was probably recognized as a good clock in about 1583. And by probably, it's because it's such a wonderful story that isn't quite confirmed unambiguously about Galileo. And I'll get to that in a second. A pendulum provides very, very regular ticks. It's an oscillating system, and I have a pendulum here. It's part of an old wind chime. So pay attention to pendula. A pendulum's a wonderful thing, and actually, sorry, I shouldn't have done that because I'm going to be talking about what's on the slide. This is a pendulum. You guys all know what a pendulum looks like. The key thing about a pendulum is that it ticks at a certain rate. It's actually quite regular. If I do this, it will swing back and forth. And the rate is only determined by two things. It's determined by the length of this pendulum. Oops, move the pivot point, oscillations die away. And it's determined by the acceleration of gravity right here. Now, on the surface of the Earth, the acceleration of gravity is pretty darn constant. So if everyone cuts their pendulum to the same length, everyone has clocks which tick at pretty much the same rate. This is the first time we have something that looks kind of global and transportable, and everyone can build the same clock. Now, okay, I showed you this. This ticks pretty slowly if you do this. If I do this, it ticks faster. Now, the other thing to know about pendula, which is kind of cool, is unless you really do this, I'll let it go. If I make a very small oscillation, it ticks at the same rate as I make a pretty big oscillation. That's a really important property, because as I make this big oscillation, pretty soon I'm going to have a small oscillation because it's going to damp down. The energy is going to go away. So what you do in a pendulum clock is periodically you kick it. That's actually the wrong place in the cycle to kick it, but the key is as it kind of damps down before I kick it every once in a while, it doesn't tick at a different rate. Those are incredibly important properties of a clock. And it allows you to make very good clocks with pendulum. Now you have to put energy into that thing or it will damp down. I showed you that you lose your oscillations. And you can build higher quality pendulums than I just did. Now you can use a weight to power the clock. And I'll show you in a couple slides how you can power your clock at the same time as you read out with a counter. Because counting that pendulum isn't going to be so easy. You can count 1, 2, 3, 4, but you don't want to do that until next week. So rate depends only on length and gravity. This is a global property. If you cut a 13.1-inch pendulum, it'll go from one side to the other in about a second. And so it's discovery. There's a wonderful story of Galileo sitting in church and being distracted by the chandeliers kind of rocking back and forth. And then saying, I wonder if that's regular. And he sat there and he timed it with his pulse. And I would suggest to you that that's not the best reference clock to use, especially if you have an exciting sermon or something. But that was apparently the origin of when he decided that pendular clocks would be a really good thing to investigate. It's not quite confirmed, but it's a great story. Huygens is a physicist who built the first really good practical devices that worked well and repeatably and really kept good time. So I have a couple cool pictures of clocks. These are actually from the Naval Observatory. And clocks of that sort, it's actually this one and this one together make a clock, were actually used as our master reference oscillators at about 1900. This was as good as you got. This guy right here is just a little more straightforward pendulum clock. There's the pendulum bob. It rocks back and forth. There's a dial. The dials are actually all separated for minutes, hours, whatever. This guy is a really interesting clock. One thing to notice is it's all in a glass envelope. One problem with pendulum clocks is it's a physical chunk of something which is defining how fast it ticks. So you need to be careful with the temperature, you need to be careful with the temperature of the air it's moving through, with the humidity. At the level of these clocks, you care about the water content of the air damping down your pendulum too fast or pulling the frequency. So you put them in little environmental enclosures. It's all a big glass jar. This guy right here is a big, well, metal and glass jar. And there's a reference pendulum in here. There's a pendulum here which is being driven so it oscillates exactly at the frequency of this guy, but this guy's really undisturbed. It's called a short clock. And that was the pinnacle of pendulum clock development. And that one would lose less than 1,000th of a second per week. Amazing clock. So I told you that pendulums tick at a very regular rate, but that's only half the story. You need to count. And that's hard, though, because you saw that if I wasn't really careful about even just holding that pendulum, it stopped oscillating, and you have to trust me, I can make the frequency change to almost anything I want to by wiggling it at the top. So you need something called an escapement. An escapement is the counter, or it's the way to get to the counter. And you'll see in a minute, that's actually what makes the tick-tock in a pendulum clock. So it provides a way to count the ticks, and you can also drive the pendulum. And the key thing is you can drive the pendulum at times only when it's in the part of its cycle where you can give it energy without messing with its rate. But it does change or perturb the rate a little bit. Perturb is just the physics word for change or alter. So here's an escapement. I should mention that this picture and the cute picture of the Earth and the sun and a bunch of other pictures I'm going to show you of clocks come out of a book called Longitude, an illustrated version of Longitude, and I'll plug the book later, but I just wanted to credit the publisher for this. So what you have is a pendulum, grossly not to scale. So this guy extends off the page. Right? I just put the little bob on here to show you that that's where the pendulum bob is going to be. And this is at one point in time, the next point in time, the next point in time. And this little thing that kind of looks like an anchor, it's called an anchor escapement, is stopping this wheel from rotating. And there's something that's trying to drive this wheel around and rotate it. And that's probably a weight hanging on a cable. So the clock is this wheel rotating, but what regulates how fast I let this wheel rotate is this pendulum bob swinging back and forth. So first this little guy catches on a tooth, and it swings over, and it hands off to this little guy holding a tooth, and that guy lets go, and it goes thunk and moves over. And in fact, at this point, it's just fallen against that hook, and it makes one sound, and then we go tick. And it probably makes a slightly different sound because of the shape of the teeth and the length of the arm and all kinds of things when it slams against this little guy that's stopping the gear from rotating, and that's their talk. That's why they sound different. Sometimes they sound very similar, but if you're a tick-tock, it's one half of the escapement and then the next half of the escapement stopping this little wheel from rotating. And it's rotating one little gear tooth along here every time the pendulum goes back and forth. So, and if you're really clever, you can design subtle things like the angles of the teeth and the way the little arms are made. So you actually put a little energy into the pendulum too. That's an escapement. And I can show you inside of a clock. This is another clock we have at the observatory. We're an old institution. We've been at the site for 125 years, so we have lots of old timekeeping equipment hanging around. This big tooth gear is the gear you just saw in the previous picture. That's the escapement gear. This drum behind it with a cable is the weight trying to turn that gear. And there's the pendulum hanging back there, and there's a little transfer mechanism, and the anchor escapement's hidden up there. The other thing to notice is there's a whole bunch of there's a big gear train set going right here. It's not very easy to see. There's some gear teeth there, some gear teeth there, some shafts going to the front. And in fact, those are driving the hands on the front of the clock. So we have ticks at some rate, and then we have a gear train so that every 60 ticks, the minute hand moves a little bit, every 3,600 ticks, the hour hand moves one notch. And now you have a clock. You have a visual counter on the front, and you've pulled the information out by using your escapement. Okay, a further refinement. Balance wheels and bars. This is just a replacement for the pendulum. It's replacing the oscillating part in the clock. And the escapements look very similar. So it's just an oscillating part is a wheel which spins back and forth, or a bar which just kind of does this. And you can have pairs of bars oscillating and all kinds of variations on that. But you can often do better than a pendulum if you want the clock to be transportable. And the key was, I need my pendulum now, you can build exquisitely good pendulum clocks so long as the pivot point doesn't move. But as soon as I start moving the pivot point, it just doesn't work. So it's often powered by a spring as well. And once you have a balance wheel clock and a spring, you can build a mechanical watch or a mantle clock or something. But you can build something you put on your wrist that is reasonably small. And the key is this is less sensitive to motions than a pendulum. So this pendulum had this temperature sensitivity, where the whole thing shrinks and swells and atmosphere gets in the way. But also if you jiggle a pendulum around, it just doesn't work. You can jiggle a balance wheel clock around much better. So a mechanical watch that you wear on your wrist, like a Rolex if you're lucky enough to own one, a mechanical one, has a balance wheel in the back. This is a big balance wheel in the back of a clock. This is actually 5 inches in diameter. It's a very famous clock for solving the longitude problem. And this guy goes back and forth and back and forth and back and forth. That's the oscillating part inside of this watch. And if you open up the back of a mechanical watch or a mechanical pocket watch, if you look carefully, there's little guy whizzing back and forth like mad, and a whole bunch of gears counting and translating into how fast the second hand moves and the minute hand and the hour hand. So balance wheels and balance bars allow us to have a transportable clock, or one that's less sensitive to motion. And now we can talk about addressing one of the really, the big clock and timekeeping application problem that's happened. And that was the longitude problem from early navigation up to about 1764. And the longitude problem is a classic problem in navigation, where if you have the Earth as a sphere, I should have brought a sphere, your distance down from the pole, your latitude, is easy to find because we're lucky enough to have a very bright star that's over the North Pole, the pole star, Polaris. And that's an accident of stellar alignments now, but it's convenient. So if you have some astronomical instruments, it's easy to find out always how far down the globe you are. But it is very difficult to find out where around the globe you are. So you can tell that you're on the equator, but you can't tell from astronomical observations if you're in South America or Africa. So it's a serious problem for shipping. The way shipping worked is you knew that the Caribbean, an island in the Caribbean you wanted to get to from Europe was at a certain latitude, so for distance down from the pole around the globe. So you went off the coast of England, you went down to that latitude, and you just went along in that direction until you hit something. The problem is you had no idea how far you had to go besides from dead reckoning. And you had no idea how far you'd gone. So you might run into Bermuda in the middle of the night and lose your ship, and that happened a lot. Or you might not realize how far you were away, and the whole crew dies of scurvy, and that happened a lot. It also makes getting lost a lot easier. So if you don't know the time, longitude's hard, and much loss of life and goods, incredible cost in life and goods. And there was a classic, well, there's a famous wreck of a naval group from England. They come back from skirmishes in the Mediterranean with the Spanish, and they were coming back, and they crashed into the side of England and lost huge numbers of men. In response to this, England offers the Longitude Prize, 20,000 pounds in 1917. It's real money, huge amounts of money. If someone could solve the longitude problem, don't care how. The test is you have to have your solution for the longitude problem and have a ship sail from England to Bermuda and back and not be off by the equivalent of a couple minutes of rotation of the Earth.
That's the wrong century.
You're right, 1867. I'm sorry. That's a typing problem. Yes, yes. You're right. You're right. You're right. I'm sorry. There's a great book about this, and the person who solved it, which is by David Sobel, and that's the book that I took many of these pictures from, the illustrated version of it, Longitude, and also Nova, the first show of this season was based on that book. And it's an interesting show. So how do you solve the longitude problem? The key is, if you know the time, you know the longitude. Because there's a complete circle around the Earth. We've assigned 360 degrees of longitude all the way around the Earth. And we know the Earth spins once a day. So we know every hour is a 24th of the rotation. That's 15 degrees of longitude. So what you can do is assume back in Greenwich that you know when noon is. That's when the sun's overhead. That's easy to determine by various stellar astronomy means. And you have a watch which is synced up with Greenwich. And you carry it and you walk over, say, 15 degrees of longitude out into the ocean. What you will see is noon will appear 1 hour displaced from noon on your watch, because it's still synced up with Greenwich over there, but you're 1 hour of rotation away from Greenwich. So you know you're 15 degrees of longitude over. In a nutshell, that's it. If you have a clock that you can carry around that stays synced up with some remote location, you know how far in longitude you are from that remote location, and you can do navigation. So there are a couple possibilities for how you would solve this problem. And one historical thing to know is that there was a longitude board set up to administer this prize. And the head of the longitude board was the Astronomer Royal of the Greenwich Observatory. And the competing methods to mechanical clocks were astronomical observations. There was a serious bias here. So first, the stellar observation possibilities. You can use eclipses of the moon of Jupiter or the lunar position of our moon relative to the stars. So you make observations, and you compile a whole bunch of observations, kind of like making a star chart. And you predict when the eclipses of the moons behind Jupiter, or where the moon relative to the stars is going to be. Now you have this big table of where they're going to be. You make observations on your ship. You look up in your table, it tells you what time it is, and you have your clock. There are a couple problems with this, first of which is the astronomy and building the charts is really difficult, especially with the tools at the time. The other is taking precise angular measurements with a telescope on a rolling ship. That's really hard. So, it's another opportunity for cool pictures. That's Jupiter. That's Io. Io. And this is a picture taken from the Voyager 1 spacecraft from about 20 million miles away. And that's the moon. And eventually it's going to go and eclipse behind Jupiter. And what you do is you would measure when the various moons, there are several of them you can see at any time, not in this particular picture, eclipse behind Jupiter. You can't see them. And that's your clock. And it's a perfectly good periodic repeating system. It's just very hard to implement. There's another pretty picture. I love this one. Well, okay, it happened to move backwards. This is Io and Europa, and that's the big red spot. It kind of shows you the scale. This moon is kind of order a quarter the size of the Earth. So your other option is something like that. That's the moon. That's the Clementine spacecraft taking pictures of the moon, 1974. It turns out getting pictures of the moon and the stars in the background is really difficult because if you want to take a nice picture of the moon, you don't ever leave your shutter open for long enough to take a good picture of the stars behind it. So you would actually see the moon as a much smaller disk on the sky with a reasonable telescope you'd carry on a ship. And you see all the stars, you see a couple of bright stars in the background, and you measure the moon's location relative to those stars, and then you have a clock as well. That one doesn't repeat really, but you can predict where it's going to be. So it's just as good. Like I said, there was a large bias towards these astronomical solutions. And in fact, no less august person than Halley of Halley's Comet said, the answer must be in the stars. And at the time when there was this competing solution I'll tell you about from John Harrison, the Astronomer Royal was a heavy proponent, and in fact did all of his research in the lunar position method, it's mescaline. And that led to a whole bunch of political difficulties later on. John Harrison actually used mechanical clocks. He decided that you should be able to build an oscillator that you can carry on a ship and will keep good enough time that you can solve the problem. And he did it, and it's kind of astounding that he did. He invented this really immense number of neat technological tricks, and despite the fact that he was basically trained as a cabinet maker, as a wood joiner. And some of his early clocks, in fact, are entirely made out of wood. And they have gold foil on the front to fake people into thinking they're brass. And there are some of his wooden clocks that are still running. Now, he has a long history of clocks that he makes. And to really hear the story, you should read the book by David Sobel. It's an excellent book. And his fourth clock does it. It takes him order of 20, 25 years and 4 clocks. He starts out with large, complicated beasts, which don't reproduce well on photographs, right? Have pictures of them with compensated balance bars, and they're kind of this big before you put them in the case, and they gimbal mount so the ship doesn't rock them. And finally, at the end, he ends up with that. This is quite possibly one of the most significant clocks ever made. It's called H4. This is fourth attempt at a marine timekeeper. It just looks like a pocket watch. It's 5 inches across, and it keeps amazingly good time. This one could be running, but they don't run it because of wear and tear on the way that it was made. The other 3 clocks he built work to this day. This guy went to Bermuda and back over order of 160 days and lost about half a minute, and fulfilled the requirements of the prize handily. It's really a triumph. And the number of things that he invented in the process of making this is astounding. He invented the roller bearing. He invented ways of temperature compensating pendulums. He invented a thing called a bimetallic strip, which allows you to compensate springs for the fact that temperature changes. Amazing number of things he invented that are used all the time in clocks. He also invented, well, like I said, this is a temperature compensated pendulum. It's a really neat device. It's alternating bars, a different type of materials with different expansion coefficients. So they expand or shrink different amounts with temperature, built in a complicated way so they all cancel each other out. And this is one of the precision timekeepers that we have at the observatory that's no longer used. Unfortunately, after he succeeds, all kinds of ugly politics ensue. And the astronomers don't want to believe it, and they think there's some magic going on inside there, and they make him disassemble it in front of his competitors. They make him build another one. In fact, the back with the balance wheel is H5. It's the 5th one he built. H4 is incredibly ornate inside, partly to disguise what it's doing, so no one could tell when you took off the back what it was doing. But finally, years and years after he really had fulfilled the requirements of the prize, by a decree of the king, he actually gets awarded the prize. So, enough with mechanical clocks. We'll go to quartz clocks and then atomic clocks. Short foray into quartz crystals. Quartz is a really interesting substance. And this is kind of sort of a quartz crystal might look like. It's a synthetic quartz crystal. It has a kind of pebbled surface, so it's difficult to see what's inside. But it's basically looks like a chunk of glass. And it has electrodes on the side. And any viewers can come up and look at it afterwards. But quartz is piezoelectric. And if you take apart the word and look at the Latin, it's pressure or pushing electric. If you squish it, you get an electrical charge on the side of it. And if you put an electrical charge on the side of it, it squishes. It's a wonderful device, wonderful substance. There are a bunch of them in nature. Now, this is really neat because you can also build a really high-quality oscillating thing. If you have it kind of shake like a bell or ring like a bell, you can make really nice bells out of quartz crystals. But the key is you can read out how it's shaking by looking at the charge on the side. And you can also pump energy into it and get it to squish and oscillate just electronically. So this means you can build an all-electronic oscillator by kind of shouting at this bell and getting it to sympathetically ring. Like if you have the music playing in your house and the piano strings start to ring, or if you have a bell and you shout at it, or a tuning fork, you can get it to ring. Or in fact, the feedback from the microphone is exactly the same process. It was the microphone talking to the speakers, talking to the microphone, talking to the speakers, positive feedback. And you build an oscillator with a quartz crystal as the kind of ringing element in there. And you can build marvelous clocks. Watches. Any quartz crystal watch is better than any mechanical watch. So your Swatch is better than someone else's Rolex. So resonance is regular oscillations. That's just saying that it's a bell. Now this displaces the pendulum in the 1920s. Up until the 1920s, the pendulum was as good as you got for a standalone clock. Now it's interesting to note, even at all these points, in the long term, you're still correcting them for stellar motion and the spinning of the Earth. And that's the real thing you calibrate everything against. But these quartz crystals allow things like really high-quality wristwatches as well. If you have a quartz crystal watch, there's actually a little tuning fork-looking thing. It's like a little Y made out of quartz crystal. And did you have a question? Or no? That's shaking back and forth at 33,000 times per second. And there's a little electronic counter in your watch which counts up 33,000 oscillations and then goes move. It tells your second hand to move. And this little stepper motor goes chunk. Moves a second. And then it counts 33,000 more times. It goes chunk. Oops, there's no transparency up there. So atomic clocks. This is what I do for a living. I build atomic clocks. They came on the scene in the 1940s. The reason they only came on the scene then is that they have to do with looking at oscillations inside of atoms. And the tools for looking at oscillations of these types inside of atoms came out of World War II research into radar. There's all the microwave research that came out of radar and the rad lab at MIT and stuff. Turns out atoms contain our best oscillators, the best ones we can find. They're the most regular. They also have a really neat property that every atom of a given type is identical to every other atom of that same type. So I can build a clock built on a certain type of atom, and it will tick at the same rate as someone who builds a clock built on that same type of atom in France or in Germany or in Brazil or anywhere. So the way we work with these atomic clocks is kind of similar to this howling feedback loop with a microphone. We have some oscillator, and we kind of shout at the atom. And once again, think of it as a little bell that will tell us if we've got the right frequency. So you shout at the atom in the microwaves, and it's kind of 4 times the frequency of your microwave oven. And it will tell you, okay, your microwave frequency is too high, too low, just right. And what you do is you then correct your little microwave oscillator so it's always saying just right. And now your microwave oscillator is just as stable as your atom. And you count oscillations of that guy. And that's your clock. It's that simple. So atomic clocks have nothing to do with nuclear power or anything. They're all kind of light bulb type energies. And you just use the fact that they're incredibly good bells inside of atoms. There are different types of atoms that you can use to build a clock, and there are different reasons you would pick a certain type of clock to build. You can build rubidium clock. Out of rubidium, it's just a metal, kind of melts at room temperature. And the key thing about those is you can build really good clocks that are kind of this big, and those are used for applications like making your cell phone better. It turns out that if you have a cell phone and you're driving down the highway, you're constantly being passed off from cell site to cell site. And what the phone company would like to be able to do is to pass off lots of these phone conversations all really well and not have you know what's happening. And the way they can do that is by having the time at each site synchronized really well. And you do that by buying little atomic clocks, and they cost a couple of $1,000s, and they're about that big. You integrate it into your phone system. There's cesium clocks. Now, it turns out that cesium-133, there's a kind of bell-like oscillation in cesium-133 that defines the second. Something the scientific community does is we have to have standards for how we measure things and how we define things. And we define things like, though, the speed of light and the second and the kilogram and things like that. And time is defined in terms of a oscillation, this kind of bell-like ringing in the cesium-133 atom. That's actually the type of clock I'm building. I'm building a clock that happens to use cesium. Hydrogen masers are another type of clock. And it turns out that if you want a clock that's the most stable for short times, it's kind of a subtle idea, but if you only get to look at a clock for a little while and you want the most reproducible ticking rate, you pick a hydrogen maser. If you wanted it to be a constant ticking rate over long times, you pick a cesium clock. So in fact, where I work, because we want the best of both worlds, we use both types of clocks and kind of average them together on a computer. Maser, actually you might want to capitalize all those letters, although it's become a word. You've heard of lasers. It's light amplification by stimulated emission of radiation. Lasers are latecomers to the field. Masers were first. That's, it says microwave.
Sir,
Yes.
many years ago they decided on how long the cycle was going to be.
Yes.
Now the Earth does not rotate 364.25 revolutions
Yep.
per year. How often and who decides when exactly is it, say 12 noon at Greenwich, England?
Okay, someone asked, how do we, if I may rephrase, how do we coordinate the rate at which atomic time is ticking and the fact that that isn't exactly the rate that the Earth spins at? And the answer is that when you decided what rate the atoms were ticking at, and you find it, you did your best job of making it match up with the Earth's rotation rate. But they do slip out from each other, and that is why you hear about leap seconds. A leap second is when you add a second at the end of the year, and one's coming on January 1st, to make sure that the Earth's rotation stays in sync with atomic time, or actually vice versa. The world's atomic time stays in sync with the Earth's rotation. It's actually my next slide. Oh, it's not my next slide. How you decide is you actually go ask someone like our Earth orientation department that's deciding how the Earth is spinning and wobbling. And you ask them, you wait until the time scales have slipped out by 0.6 of a second. You add a second, now you're 0.4 on the other side, and it decays away. And we add a leap second every year or so. Answer your question?
Yeah, but how do they decide exactly when is it? You know, what do they go by to decide, well, you got to add a second or take away a second?
Okay. How is the decision made for when you do it? It turns out there are international agreements on both what time it is and how the Earth is spinning. And that's a big scientific collaboration, data collection endeavor. And it's done by an organization called the BIPM, International Bureau of Weights and Measures, if you construct the acronym in French. And you just wait till the scientific consensus is we're out of step by about 0.6 seconds. And then there's only a couple times a year where they're allowed to be added, and January 1st is one of them. And you say, okay, next January 1st, we're going to do that. And you announce it 3 months beforehand, because you can tell when you're going to cross that line pretty well. The spin down rate of the Earth is pretty predictable on that scale. The short answer is that you ask all the scientists you can for all their data, and you decide when it's out of sync. Part of what you asked was a political question, though, and various people have different ideas about how that should be done. Okay, world timescales. The world also decides what time it is, and a key to know is that time is at a really basic level a voted quantity. Let's say you have 2 clocks. Well, let's say first you have 1 clock. It may be doing something really weird, and unless it goes out weird enough that some other clock, like the sun coming up, doesn't agree, you'll never know it. You know, so you have 2 clocks, and you can compare them. You're really maybe even worse off, because if one clock doesn't agree with the other, you don't know which one to blame, unless someone hit one with a hammer or something. So you have 3 clocks. Now you got a fighting chance. Now you can throw out the oddball if the other 2 agree. And you do better by averaging more and more and more clocks. And so what has been decided amongst the scientific community and international treaties and all that is everyone sends their clock data to an organization in France called the BIPM, and they average all the numbers, and they produce what time it is as defined for the world. It's called Universal Coordinated Time. It used to be called Greenwich Mean Time. It has a new name now. And that time is basically atomic time, and then you add the leap seconds to make sure it stays correct with the rotation of the Earth. An interesting thing is that you send all your data to the BIPM, and they crunch the numbers for a while, and they tell you what time it was because they have old data, right? So you find out what time it was from them 30 days ago. One of the things we do at the Naval Observatory is we actually produce our best guess of what time the BIPM is going to say it is now, because that's what our users care about. They don't care about what time it was. They care about what time it is now. This is a bunch of atomic clocks. These refrigerator-looking things are environmental chambers because we have to keep them in temperature and humidity stabilized environments. Each one of these little boxes with some red dials, red lights that you can't read, but which are all reading the same time, are each cesium clocks. You can buy them from Hewlett-Packard. So there's 8 clocks here and some power supplies and things. They're not very photogenic. Okay, I actually have only 3 more slides. The last thing I'm going to talk about is probably the pinnacle of applications for atomic clocks. It's called the Global Positioning System, or GPS system. And it was envisioned in the 1970s. The design was basically fixed in '73. And it's an amazing system. There are 24 satellites in orbit around the Earth. They orbit twice a day. And they all have atomic clocks on them. They either have 2 or 4 atomic clocks. And they're all kind of shouting at you and telling you what time they think it is. Now, you know that the signals they're sending down at you, they're microwave signals, are traveling at the speed of light. And that, coupled with where they are, and the constellation also tells you exactly where all the satellites are, allows you to kind of calibrate some delay from the satellite to you. But you know that delay was being traversed out at the speed of light. So you have some kind of yardstick from you to that satellite. But you don't know where that satellite is, maybe somewhere like this. Actually, no, the problem is you don't know where you are on the end of that stick. So then you get another satellite, and another, and another. And by the time you have 4 satellites, and you have yardsticks to kind of 4 satellites, you can tell where you are on the surface of the Earth and what time it is. It turns out you need 4, and you have to know what time it is, the way the system works. And it's amazing. You can find out your location to about 100 meters, 100 yards, for about $100. Because of these billions of dollars worth of satellites up in orbit, you can buy one of those things, and that is a $100 GPS receiver that will tell you where you've been along your hike and where you're supposed to go in the direction you were heading last, and where you are to 100 meters anywhere in the globe, so long as you can see the satellites. The only reason you wouldn't be able to see the satellites is if you're covered with snow or tree leaves or some kind of water that actually absorbs the microwaves. That's a picture of the satellite. It's not a great picture, but it's the only non-copyrighted one I could find. These are solar panels. This is about as tall as a person. This is a big antenna array. So this is talking to you in the microwaves, telling you what time it is. And the US government saw fit to put a whole bunch of those up in orbit. So that's basically my talk. Hopefully I've told you what a clock is, why we wanted them in the first place, a couple of the real highlights of applications, and maybe motivated why we're keeping to do it. Better location, better communications. And the last thing I'll leave up before I ask for questions is what I think the most significant clock and humbling clock I've found. Thank you for your attention.
Thank you very much, Doctor. It's been fascinating. Are there any questions from the House for the doctor?
Yes, I have a question here.
How do you compensate for the leap second in the satellites?
Question is, how do we compensate for the leap seconds in the satellites? Each of the GPS satellites has a whole bunch of information uploaded to it every 12 hours. And it knows about all kinds of things like what we know about its orbit and what we know about its clock and how to correct that. And when the leap second is coming, we just upload the information. We don't. The Air Force does. And the satellite knows about it in plenty of time to just account for the leap second. Yes, another question?
Yes, on shortwave, I pick up the coordinated universal time. Is that the most accurate time that I can get?
The question is, on shortwave, he gets the universal time, and is that the most accurate time he can get? I'm not sure what the frequency is for that. Is that 60 kilohertz?